Hey guys, this is Joe again, and I'm going to go over KCL problems. I had some people asking me about that. So what I'll do is go through example 1.1 in our book, which is the 5th edition of the Fundamentals of Electric Circuits, and that's by Charles K. Alexander. Now, some might have the 3rd or 4th edition of this book, and that's absolutely fine. I found in my past experience that the books are really similar. The only thing that may be different would be that there may be a typo in another book that they fixed in a new edition, or your homework problems. For example, problem 5 in the book could be problem 6 now, and they could have just swapped, or 11 could be 5. Just however they found fit to teach you guys and understand that. Other than that, the biggest thing is what they did is just change the numbers. So you might have had a 1 ohm resistor that might be 10 ohms or 5 ohms now instead of that 1 ohm. So that being said, let's go ahead and follow this example 1.1 in the 5th edition, and we'll get started. So basically in the 5th edition, we have this circuit here. This is on the way that they draw the circuits for the most part. Now, it's not my favorite way to do it. I'll show you how I draw the circuits, which you guys can see right here, and I'll explain why. So in this situation, we have a ground node here. This ground node actually shares this whole entire section here. So that means that this 3-volt source is tied to ground, the 5-volt source is tied to ground, and the other end of the 8 ohm resistor is tied to ground. So instead of doing a huge circle and doing that, the way that I draw is like so, which is just showing 3 separate grounds, which in reality they do share ground. When in fact you think about ground and what that is, it just means a 0 potential. There's no potential there, so 0 would be what you start with, and that's exactly what we're giving, which means that all 3 of these would be the same. Now we're going to use KCL, which we can tell in these currents here. So what goes in must come out. So basically what that means is that the sum of all currents, it would be 0 from any node. Basically, like I said, what goes in must come out, so that law may hold, which is KCL. Now, the thing that you got to think about with KCL and KVL, it's kind of backwards. Usually when you have a KVL problem, Kirchhoff's voltage law, you're going to solve for some sort of current. And if you have KCL, which is Kirchhoff's current law, you usually solve for some type of voltage. That being said, let's go ahead and show you what I mean by that. So at this node, VA, that we just arbitrarily made up, we would like to know what the voltage is there. Because if we know what the voltage is there, we would easily be able to find out what the current is, and we'd be able to find out what the power dissipated through each one of these branches may be. So that being said, let's go ahead and move on to the actual problem. I went ahead and color coordinated the current going through the 2 ohm resistor as orange, the current going through the 4 ohm resistor as purple, and the current going through the 8 ohm resistor is green. And we can start with the KCL problem. And here's our node again, VA. So what we would do is take the voltage difference between each node. For example, if we were going through the 8 ohm branch, we know that VA minus whatever voltage is on this side, which is ground, so VA minus 0 over 8 will give us the current over the 8 ohm resistor, or we could call that I8 ohm in green. And VA minus 5 volts over 2 ohms would be the current that would go through the 2 ohm resistor. Now the tricky part about the 3 volt, which this isn't drawn correctly, but the 3 volt is that it's minus plus, meaning the plus is grounded, so this was our 0, and the minus part is actually touching the circuit. So what that means is you're actually getting minus 3 volts here and not 3 volts itself. So what we'd want to do is take the voltage difference again, which was VA minus negative 3 over 4 ohms, and we just repeat the process and say that is equal to 0. So that being said, we got I2 ohms right here in orange, which means that we got VA minus 5 volts over 2 ohms. And then we have our purple, which is our 4 ohms. We got VA minus, and like I said, minus 3 volts over 4 ohms. And then our last color, which is green, we got VA minus 0 over 8 ohms. And this is all equal to 0. Like I said, we're just representing I2 ohm in the orange, I4 ohm in the purple, and I8 ohm in the green. Alright, so an easy way to do this is just move everything that is not related to VA to the right hand side. So if we have VA, and you have 1/2 plus 1/4, 1/2 is an orange, the quarter will be part of the 4 ohm process, and the green is the 8 ohm, so that's 1/8. And that's equal to, well, we have two numbers that we would have to move, 5/2 and 3/4. So you got plus 3/4 and plus 5/2, so it's 0.75 and 1.5. So on the right hand side we can say plus 5/2, and we can also say minus, because this minus and a minus is a plus, so then when you move it to the right hand side it would be minus 3/4. Now basically, if you want to put these in the same type of denominator, you can just say, okay, you got 10/4 minus 3/4, so then that's equal to 7/4. So what we'll do is just say 7/4 here. Alright, so we got 7/4 is equal to the stuff on the left. Basically, to get a common denominator, if you just multiply everything by 8 on both sides, would get rid of everything on the left and make it an actual whole number. So that's actually going to be VA divided by 2, which is 4. So you got 4 VA plus, and then you have 8 divided by 4, which is 2 VA. And then you got 8 VA over 8 VA, which is just VA. So then you got 4, 5, 6, and 7 VA. And then you have, so we got 7 VA, and that's going to be equal to 7/4, but then, like I said, we multiplied this, and the 8 divided by 4, which is 2, and 7 times 2 is 14. And then we got VA is equal to 14 divided by 7, which is equal to 2 volts. Oh great, that's going to answer everything pretty quickly from this point forward for us. So what we have is our currents through the 2 ohms, the currents through the 4 ohm, and the current through the 8 ohm. And we know that this is equal to VA minus 5, which was our equation earlier, over 2, which is equal to 2 minus 5 over 2, which is equal to negative 3/2. Like I said, we picked the current to go in this direction. What that means is the current is actually going in this direction. Okay, so the current through the 4 ohm was VA minus negative 3 over 4. And that's equal to 2 plus 3, which is 5/4. So we did get the current direction. So I through the 4 is equal to 5/4 of an amp. And then we got I8, which is just 2 minus 0 over 8, which is 1/4. So basically we got I8 ohm is a 1/4 amp, I4 ohm is 5/4 of an amp, and I2 ohm is minus 3/2. Okay, great. So basically the other thing we can find out too is power. And we know that power is going to be equal to V squared over R, or you could also say it's I squared R. We know any one of these two, basically you can figure out the rest. And for example, I'll just go over one example of maybe the 4 current through the 4 ohms. So then you got 5/4, which is your I squared, times R, which was your 4 ohm. So then basically you get something like 25 over 16 times 4, which is equal to 4, 8, 12, 16. So basically 25/4 watts through the I2 ohm, I4 ohm. Yeah, the I4 ohm is 25/4. Alright everyone, I want to thank you for watching this video. If you have any comments, please leave them below.